Hello viewers, welcome to MAGESH classes. In this presentation we are going to discuss about the coordination chemistry concept. It is the TRB Booster-3 videos. Let us move into the question part. The question is, the correct order of wavelength, that is lambda max, of the halide to metal charge transfer band of the given complex. The given complex consists of the halide ions, chlorine, bromine and I. What is the correct order of the wavelength, lambda max? What is the concept? From the spectrochemical series, the splitting order is like that. So it is from the spectrochemical series. Hence the order of energy CFSEs in the given complexes, chlorine splits more. So that the octagonal complex, this complex having more splitting energy than bromine complex, than the iodide complex. So this is splitting order. We know that the energy del E is equal to, in joule, H. The energy del E is equal to H into C by lambda. From this equation, higher is the energy is greater, the wavelength is lower. So greater is the energy, the wavelength is lower. So from that we can observe the correct order of wavelength is the iodide having higher wavelength because it has lower energy, splitting energy. Iodide complex having wavelength, higher wavelength than that of the bromide, then the chloride. Clear? Let us discuss the next question. Among the following metal carbonyl species, the one with the highest metal carbon backbonding. So it's a backbonding concept. Backbonding is between the metal atom and the ligand donor atom. So in case of complexes having positive charge on the metal, positive charge is present in the metal, what happens? The backbonding is decreases. Here, negative charge is present, then only the backbonding is greater. So backbonding is nothing. It is the donation of electron metal to the ligand atom. So greater is the negative charge. The metal ligands, the carbon backbonding is greater. So that the metal carbon backbonding is greater in the complex with a higher negative charge. Here the negative charge is greater in the titanium CO6-2 minus complexes. So the answer is C. So positive charge is greater, the backbonding is lower. Negative charge is greater, the backbonding is greater. This is the concept. Let's move into the next question. The correct order of del O, the octagonal CFSE, values for the following anionic metal complexes. The various anionic metallic complexes, iridium, rhodium, and cobalt complexes are given. What is the concept? Here the CFSE depends upon ligands and the d orbitals. How the CFSE depends upon the d orbitals? For the same group, the octahedral crystal field splitting energy varies within the group like this. 3D 4d, 5d. That is, in the d orbitals, in the fifth orbital is higher splitting than that of the 4d orbital. And in the case of ligands, it is given by the spectrochemical series. The increasing order of splitting ability of the ligands are given in the spectrochemical series. Now come to the question. Here the complexes, the metals atoms are iridium, rhodium, cobalt. These are in the same group, cobalt. It is in the 3d case. It is electrons in the 4d orbital, in iridium 5d orbital. And in case of ligands, the splitting orders, we have known that the cyanides and the halides. The splitting ability of cyanide is greater than I ligand, cyanide. Okay. So the CFSE order may be the cobalt metal is in the 3d level, CO, and the ligand I6, 3 minus. Then rhodium. Rhodium, there are two complexes here. One is a cyanide and one is a iodide. So I6 is first. Then cyanide. Then iridium. IR complexes 3 minus. So this is given in the order COI6, then rhodium, CN, and rhodium I6 is given. So this one. Here the cobalt 3 minus, rhodium I6, rhodium CN, and iridium CN. So the answer is B. Clear? Let us move into the next question. The crystal field stabilization energy CFSE in the magnesium aqua complex. What is the CFSE? In this complex, the manganese is in the +2 stage. Oxidation state of manganese is 2. It is D5 system, that is 3D5 4s2 Mn+2 D5 system. And the given ligand H2O is weak ligand. In the presence of weak ligand, the d orbital split into 2 level. One is it is weak, and so the electron field like this. First electron, third electron, fourth, fifth. It is 2G3, Eg2. So the energy is lowered by minus 0.4. It is increased by 0.6. Del 0. So by calculating, the CFS is equal to, so it is minus 0 CFSE value. So the answer is A. Clear? Okay, viewers. Up to this we have stopped this presentation. Thank you for listening.